I'm here to present my project SeaGuard MARL, a multi-agent reinforcement learning for cybersecurity simulation, which is a comprehensive framework for real-time network defense strategies and system architecture. The aim of this project is to develop a cybersecurity simulation system that uses multi-agent reinforcement learning, where multiple AI agents work together to defend a network from cyber attacks. This framework does just react to attacks from but learns and adopts improving its defense strategies over time. Its intelligent, research based approach combining machine learning, cybersecurity, and system architecture. So, the second slide is the table of contents. Here's an overview of the presentation. I'll start with an introduction to the SeaGuard MAL framework and its key objectives. Then I will explain the technology stack used, following by the overall system architecture and its object-oriented design. So the first is the overview of the paper, the second is the technology stack used for our project, the third is the architecture diagram, fourth is the object-oriented nature of the implementation, the fifth is the class diagram, which is a very important thing, and the sixth is the mathematical foundation which is used, and the sixth is the data flow between components, and this last one is improvements made and the conclusion. So this is the simulation overview of our project. SeaGuard MAL is designed as a cybersecurity simulation framework which uses reinforcement learning techniques. The core idea is to explore how multiple AI agents can coordinate or act independently to protect a computer network under simulated attacks. It compares cooperative learning where agents share information or act independently to protect a computer network. This setup helps researchers understand which strategy is more effective when responding to real-world cyber threats. The system can also visualize defense behaviors in real time, making it easier to observe how the AI responds to attacks. So that is what is concluded in these five parts, which is introduction to our project, that is SeaGuard MAL. The second is comparison of defense strategies. The third is the technical implementation. The fourth is the key features of SeaGuard MAL, and the last one is exploration of multi-agent reinforcement defense approaches. Yeah. So this is the technology stack and the development tools which is used to develop our project. The first is the programming languages used. So the main language we used is Python for backend logic and reinforcement learning agent training. JavaScript for front end, as JavaScript is just used to make the web pages interactive. The second is the simulation and machine learning frameworks. Microsoft Cyber Battle Sim as a simulation environment for network cyber operations. PyTorch performing MARL algorithms like MAPO and IPO, which stands for Multi-Agent Proximal Policy Optimization and Independent Proximal Policy Optimization implementations. Yeah, the third is the frameworks for backend, which is Flask with Flask Socket IO for backend REST API and real-time communication. The fourth is the development tools, which is a Visual Studio Code where we write the code, and npm for code editing and package management to install the required packages, and virtual env for Python, as we keep up what do we say we keep an isolated environment for our project, that is called the virtual environment, so that it won't be clashed with the global environment of Python in simple. The fifth is the front-end interactive framework, which is React with React Flow to enable dynamic interactive network topology visualizations. The last is deployment and data management, like scenario data stored as JSON files, which is JavaScript object notation files, where the data is written in the form of key value pairs. Train models saved locally in .pt format. Deployment designed for local execution with Docker container ready readiness for scalable environments. So this is the final system architecture. It connects all components, the React front-end, Flask backend, and the Cyber Battle Sim environment. Now I'll explain how it works. The user starts a simulation through the front-end, specifying the network topology or scenario parameters. The backend, the Flask API, then triggers Cyber Battle Sim to create the environment and deploy the agents. Here, each agent observes the environment, takes actions, and receives rewards based on how effectively it defends the network. The results are continuously sent to the front end using real-time updates like Socket IO, allowing users to monitor the agent's defensive behaviors over time. This architecture ensures scalability, modularity, and responsiveness in the project. So here is the sixth slide, which is object-oriented class structure for our project. This implementation follows a strong object-oriented design to maintain modularity and clarity. The system is divided into four key components or four key types of classes, which is agent class, which defines the AI logic. Each agent has its own policy and critic networks that decide what actions to take. The second is the environment classes, which connect to cyber battle sim, manage infection states, and handle alert logics. The third is the controller classes, which acts as bridges, managing API calls and the flow between the user inputs and simulation outcomes. The last is utility functions management, which handles tasks like configuration, hyperparameter tuning, and reward calculation. This overall structure makes the code which this overall structure makes the code readable, reusable, and easy to expand for future improvements. Okay, so this is the class structure of a backend system, or simply the class structure of a project. So there is nothing much, it's just a diagram like how what are the things we have used and what are the parameters we just have defined. So you can just go through this. So the this slide, which is the mathematical foundation of SeaGuard MARL, this slide highlights the mathematical foundation. The agent's goal is to maximize its expected reward represented by the function j of phi overall this function, which is difficult to speak, okay, sorry, which calculates the cumulative rewards over time. The proximal policy optimization, which is PPO algorithm, is used here. It helps balance learning speed and ability to limiting how much the policy changes in each step. In MAPO, which is multi-agent proximal policy optimization, a centralized critic evaluates all agents together, promoting cooperation. In IPO, which is independent proximal policy optimization, each agent has its own independent critic acting alone. We also use generalized advantage estimation, which is GAE, to reduce how noise is training and improve performance and consistency. These formulas together form the learning engine of the entire system, which is collectively called as the mathematical foundation of our project. Oh, sorry. So this is the data flow between the modules. Here's how the data flows. So first, the React, the front end sends an HTTP request, which is to the Flask API when a user starts or modifies a simulation. Next, the Flask backend creates a simulation thread that runs Cyber Battle Sim, initializing the environment and the agents. During execution, Cyber Battle Sim processes the environment state, handle attacks and defense actions, and updates infection levels. The backend then sends real-time updates to the front end using socket IO events. Finally, the front end dynamically updates the network visualization, showing live changes in agent behavior, node status, and overall defense performance. So that is what is explained in the overall 5 steps, which is React front end initialize data exchange, Flask, which is the backend manages the simulation, the third is Cyber Battle Sim processes environment, the fourth is real-time data emission from Flask, and the last is React frontend, which visualizes the updates. So this is the architectural improvements for our project. Integration of React Flow provides an intuitive and interactive network topology design experience. Implementation of Flask Socket IO, embedding Microsoft Cyber Battle Sim, introduction of modular design, and addition of persistent scenario storage. So I'll explain each and every one. So persistent scenario storage using JSON files allows experiments to be saved and reproduced. In case of modular design, with separating MAPO and EPO agents for better control and tuning. Real-time feedback using Flask Socket IO for instant visual updates. Integration of Microsoft Cyber Battle Sim, which brings realistic and detailed attack defense simulation. This upgrades makes the framework more efficient, flexible, and close to the real-world cyber security cases. So thank you guys. This is the total project. So this is the demo of my project SeaGuard. So I'll just start with it. I'll go to type cd backend to go to the backend root. Then I will run my main Python app. It's Python 5. Okay, the app is running successfully. So I'll open a new terminal. So first I need to go to this root env virtual environment, then the scripts, then I'll type activate. Okay, so I'll just type R to run once. So now I'll go to my front end root. Okay, after going here I'll just do npm tab. Okay, so I'll just do control click, my app will open. So this is what it actually looks, the interface of a project. So I'll just take all my 4 components. Okay, this is double, we can just keep this aside. HMI, I'll just do a reload. PLC, HMI, I'll just keep this over here. Uh, sorry guys, 1 2 3 4. Okay, where is the server part? Okay, I can just do the connection in any way. So mm, just keep this a bit low. I'll just do this connection. So the connection part is done. I'll run the demo using Mapo. Then I'll just show you with IPO also. It takes time. That's it. Mapo completed in 14 steps. This yellow indicates that the attacker is is about to attack on this component. Yeah. If I'll just swipe it with IPO and I'll run the demo. Yeah, it took 37 steps, whereas Mapo took around 14 to 17 steps. So Mapo performs better as it consumes less number of steps, and everything is green, which shows everything is fine. Yeah, and this is the overall project. Thank you.